Good morning and thank you for being here. My name is Nadja Gaudilliere. I'm a PhD candidate at the GSA laboratory and I'm here to present my work, Computational Tools in Architecture and Their Genesis, the development of agent-based models in spatial design. This project is part of my PhD research, which is a contribution to a history of the computational turn in architecture. In particular, I am interested in the confrontation between tacit and explicit knowledge at play in procedural design processes. In opposition to the explicit, tacit is a form of knowledge that cannot be formalized and is therefore hard to transmit. It is inherent to practices such as architecture, making those particularly difficult to automate. In the field of computational architecture, it is sometimes referred to as empirical decision-making, or, as Christopher Alexander puts it, the quality without a name. What appears to be particularly interesting in the computational field is the confrontation of the tacit knowledge inherent to architecture with algorithms requiring an entirely explicit set of instructions for the computer to perform its calculation. The present research focuses on multi-agent systems as a case study, for they are emblematic of one of the two approaches to this tacit-explicit confrontation characterizing the computational term. In order to perform such a study, I've developed a methodology drawing on science studies to assess the computational turn in architecture. I've used as a corpus of projects references made to computational design projects in AD magazine since 1965. For a more recent assessment of the computational practices in architecture, I've looked at the Acadia Communicate paper database. From these two lists, I have extracted the project mentioning multi-agent systems, which I have documented further by having interviews with the practitioners and looking at public and private archives. My goal is to document three aspects: the historical development and the network of development of the computational community, development of multi-agent system tools in this community, and the trade-off between tacit and explicit at play in projects performed with multi-agent systems. This last element is being assessed by observing four areas: architectural design, organizational chart, algorithmic tools and method, and computational setup. As I mentioned, multi-agent systems are emblematic of one of the two approaches to the tacit-explicit tension in computational design, but this approach is also rather specific to a period of time. The computational turn can be characterized by a series of computational generation, each with a given group of practitioner and institution, specific tools and technical setup, and a distinct manner of using computational tools and of understanding the contribution of these tools to architectural design. The two first generation are characterized by expert system and 3D modeling, and have been the moment of constitution of the network, constitution of the field, and theorization of the possibilities of computational design. The third and fourth generation are emblematic of the two major approaches that can be observed in the field: an appropriation dynamic on one hand and a rationalization dynamic on the other hand. The multi-agent system typology inscribes especially well into the third one, and what I'd like to discuss today is why, while being so well suited to that period, they have appeared to be less well suited to the fourth generation, which also corresponds to the democratization of computational tools. Before diving into that issue, I'd like to give a brief reminder of what multi-agent systems are. They are object-oriented algorithmic systems modeling the behavior and interaction of sets of agents. Each agent is obeying a series of given laws, and their interaction generates emergent behaviors. In the present research, I have identified them as one among several typologies of algorithms in use in the computational field. A typology means a predefined set of instructions identical for all algorithms of the typology. For the multi-agent system, these sets of instructions are separated in three levels of rules: the ones pertaining to the initial state system, the behavioral rules, and the geometrical exploitations once the interactions are over. At large, in the examples from the corpus studied, the multi-agent system is used for three goals: almost always shape generation, structure generation in 2/3 of the cases, and more rarely space hierarchizations. Here are a few examples of use of multi-agent system in order to produce architectural design by Kokucha, Supermanœuvre, BioThing, and Plethora Project, all founded by practitioners of the third generation having contributed to the development of multi-agent systems in the field and to associated algorithms and tools. This generation is marked by an especially high level of programming skills, allowing for the development of algorithms tailored to the objective of each project, also allowing for a strong bias awareness and for a skillful negotiation of the tacit-explicit tension with a conscious capability to translate tacit knowledge into explicit algorithmic instructions. This generation is also characterized by a back and forth between the development of algorithm, tools, libraries, and a classic practice of architecture relying on this tacit expertise and mobilizing these algorithmic tools in a classic way that would any other tools be mobilized. This can be interpreted as a successful appropriation. The generation described earlier can be understood as what Bruno Latour calls a socio-technical network that has broadened and densified with each generation. For each typology, including multi-agent systems, a subnetwork can be identified by listing the practitioners resorting to multi-agent systems, the tools they use to do so, the practices and the institution they are part of. Pictured here is a core network of multi-agent systems at the beginning of the third generations, with each clusters of development that have led to the current mode of existence of these typologies. A few remarks can be made in particular when comparing to other typologies networks. Here we have a network of practitioners traveling between institutions rather than institutions being at the center of the network. We also note an absence of the industry, in particular compared to genetic algorithms where the industry came into play soon and contributed majorly to the development. We see little cluster of tools except a cloud of Grasshopper plugins, much else being done in existing multi-agent frameworks by developing tailored algorithms. These remarks combine into one further observation, the difficulty for the multi-agent systems to exit this core network, an exit that is key to the phenomenon of democratization happening in the fourth generation. In the case of multi-agent systems, the study shows little spread beyond the students of the institution and people already present in the core network. It also shows little spread beyond the academic field. In comparison to genetic algorithms, which manage to exit the core network and to be made available to a greater number of users, the multi-agent systems remain at large in the hand of the practitioners highly trained in programming, characteristic of the third generation. Where I've discussed the emergence of a dynamic of democratization in the field, skilled practitioners remain a minority, as the number gathered on the left side demonstrate. The use of multi-agent system remains in the hand of users, and multi-agent systems tools do not exit to potential pool users, unlike the genetic algorithms, which have done so by being integrated in several softwares automatically. The general dynamic of development in the field I have attempted at representing in the graph on the bottom, where multi-agent systems stay in the blue skilled practitioner area. On the opposite, typologies that have managed to exit the core network would also develop much further into the pink users area. What this graph also points to is the variety of user profiles and the importance of that variety to understand the democratization issue. The user developer difference must first be pointed, in particular given the fact that it's often shown off as a characteristic of the computational field, with architects seizing again the possibility of making their own tools, a possibility that, as I have mentioned previously, encourages the appropriation of computational tools and the implementation of tacit knowledge. This possibility is associated with the capacity to draw from other fields. As is shown in the chronology, this is the case with multi-agent systems, whose apparition was enabled by the appearance of object-oriented programming, fostered in the field of animation, and then taken on by architectural design. I also mentioned the capacity of the third generation to create what I call tailored custom algorithms, but with democratization we have also witnessed the appearance of ready-made tools, easing the resort to typologies. We can assess three categories of ready-made tools depending on the facility of access of the typology: plugins necessitating to be downloaded, plugin built-in in software, and function directly integrated into software. For multi-agent systems in computational design, the very large majority of tools available are of the first category, therefore not extending to a larger potential user pool. The ease of use of a tool is key to this in terms of democratization and relies on two elements. First, the ease of understanding the structure of the model on which it relies. In the case of multi-agent, the algorithmic structure of the typology and its associated rules. And second, the ease of use of the interface. Part of the present research is the analysis of multi-agent systems tool interfaces and their thickness. The thickness of an interface is a notion developed in the field of UX to assess the distance between the elements a user can manipulate and the actual structure of the program, and can be expressed in a number of layers. In our case, the thickness of interface acknowledges the varying distance between the initial architectural intention and the final representation that is the output of the algorithms. The variation of thickness is intricately connected to the ability of the user to access rules and details of the mathematical models, and to the similarity of knowledge profile of users and developer. Therefore, in the third generation, users are in their majority capable of scripting and tailored algorithms and to devise their own libraries and interface. The knowledge profile overlaps, thus providing almost zero thickness interfaces for multi-agent systems. Tailored algorithms enable an access to rules in upper layers and are composed of a small number of layers, while, as you can see on the slide, ready-made tools are composed of many layers and the access to programming of specific rules is located in lower layers, harder to access for users with little programming skills, and leaving upper layers with only predetermined behaviors. Thus, the second phase of development of multi-agent systems is characterized by interfaces with high thickness, hardly enabling a detailed manipulation of the typology and hindering appropriation through tacit implementation, which is a step crucial to the use of multi-agent system given the complexity of this typology, and therefore hinders also their further democratization. In conclusion, the present research relies on the development of methodology for a comprehensive understanding of multi-agent systems in computational aided architectural design, providing a contribution to the history of computational design tools. The development of multi-agent systems in the field is examined in regard to three dynamics, showing excellent appropriation, maintaining the major issue of neglecting the tacit dimension of architectural practice at bay, but proving difficult to fully democratize. A further hypothesis I'd like to make that would need further research is the possibility that multi-agent systems rely on different fundamental units than the current constraints put in place both by the software and the construction industry, and this is the basis of a clash preventing the full assimilation of multi-agent system by the field. While a simplification for an interface easier to manipulate is the key to the democratization of algorithmic design tools in architecture, tactics of tacit explicit negotiation depend in a large part of the understanding of tools by their users, and biases enabled by the structuration of algorithmic typologies, of tools and of interfaces necessitate broader studies and awareness. Thank you for listening.